Good afternoon. It's my pleasure to discuss the results of my studies today. My name is the topic of my presentation is shown in the picture. Generally, it concerns determination of the basic microstructural parameter in the gurson tvergaard needleman material model. As we can see in the first picture, typical steel used in technique is not pure. It contains some other particles, especially carbides, manganese compounds, oxides, and many others. During plastics training, these particles are the initiators of voids. The scheme of void initiation and development is shown in the second picture. So first of all, we have nucleation of voids, and here we can distinguish two basic mechanisms. First of all, we have the decohesion between the particle and the surrounding matrix, and secondly, we have the particle cracking. As the plastic strain increases, the voids grow. Here we can see it. These voids then coalesce and finally lead to formation of macroscopic defect and failure of the structural element. In the literature, we can find many models that describe plastic material behavior in terms of development of voids. But I focused on the gurson tvergaard needleman material model, in short the GTN model, and now I'd like to explain why. First of all, this model is recommended by the Eurocode standards for analysis of structural members operating under pre-failure conditions. And secondly, this model is implemented in many computer finite element method programs. So this model can be used for for analysis of structural elements. I'm an engineer, so I look for solutions which are useful from the engineering point of view. That was why I have chosen this model. In the GTN model, a parameter of void volume fraction is included. It's defined as the ratio of volume of voids to the volume of the whole sample. And this parameter plays the role of the softening parameter. So it gives us the possibility to model the reduction in load carrying capacity shortly before failure. Other models based on material continuum assumption cannot do this, and this is the biggest advantage of the model. The GTN model is described by the following equation. Here we can see many parameters, but I would like to draw your attention to the volume fraction of voids, which is some kind of novum in this model. It's worth noting that if we neglect the volume fraction of voids, the GTN criterion reduces the classical Kuber-Misas solution. The change in void volume fraction during the loading process is described by the following equation, but for me now the most important is critical void volume fraction at the moment of failure, which is denoted by FF. And my task is to determine the value of this parameter experimentally. Of course, the problem of parameters identification is not new. Many other authors did it before, but the basic rule is that they choose the parameters in order to provide convergence of experimental and numerical results. And that's the only one criterion. They didn't pay attention to the microstructural phenomena described by the model. So simply they choose the value to provide the convergence with the experimental data. I want to determine the value experimentally. So it's a new kind of approach, and this is it. Of course, we have many other values given by other authors. The value of FF ranges from about 10 to about 70%. The program of investigation involved tensile static tests of the specimen with a notch. The dimensions and the shape is given in the third picture. The presence of the notch produced complex triaxial stress states in the specimen. S355 steel was used in the investigation because of its wide use in engineering. Here we have the specimen subjected to tension. Force and elongation were monitored during the test. The test was performed up to failure. Secondly, in order to determine the value of the critical volume fraction, microscopic analysis of fracture surface was performed. This is the specimen after the tensile test. Here we have the fracture surface, and this fracture surface was subjected to microscopic investigations. Microscopic photographs were made. The magnification was about 10,000 times, and we obtained the photographs of the fracture surface. The next step was to assess the void volume fraction as the fraction of this darker area. But maybe I will explain it in a little bit different way. The white regions here were assumed to represent the intervoid alignment at the moment of failure. Secondly, these darker areas were assumed to represent voids. And the next step was to binarize the photograph, which I mean by dividing the photograph into two parts. Basing on the grayscale criterion, I divided the photographs into areas representing voids, the darker ones, and representing the intervoid fragments, which are the light areas in the picture. So here we can see the photograph after binarization. Colors here are reversed, so now the intervoid ligaments are darker, and the next step was to delete the areas representing voids in the picture and to calculate the areal fraction of these deleted areas. The procedure described above made it possible to obtain the value of FF equal to 0.598, which is rather high value. I would like to remind that the values given in the literature range between 10 and 70%. So it's rather much, but it's worth noting that this analysis was performed for low stress state triaxiality ratio, which was about 0.5. I tried to deal with the microstructural phenomena and to connect the phenomena with the model parameter. But now it's time to answer the questions. If this value and the GTN model produce good results. To answer this question, I performed the simulation of the tensile test performed before. Here we can see the model. Because of the symmetry, only one half of the specimen was modeled. That was the axisymmetric model. The GTN model was used. Here we have some parameters of the model. Some of them were derived from the literature. Some of them were measured by me. And in the next picture, we can see the experimental and numerical results. This is the force versus elongation. As we can see, the GTN model and the parameter determined experimentally provide good convergence of simulation and experimental data. The next picture is derived from my other paper, and it shows the effect of stress state triaxiality on the FF parameter. So we can see that as the triaxiality increases, the FF also increases. But I have to say here that this triaxiality ratio is the initial ratio. Of course, it changes during the loading process due to the deformation of the specimen. So to conclude, I can say that the value obtained during the experiment was in the range described by the literature. The GTN model and its parameters gives us the possibility to simulate plastic deformation in good way. Thank you for your attention.